So the topic for today's presentation is like fast and the furious CICD pipeline for eBPF programs at meta scale. Basically, I first want to start by setting up some context for the talk. These are all the people who are involved in developing and supporting our net-edit binary, which basically manages and deploys a bunch of eBPF programs across various attach points, doing multiple tunings for packets and connections, and also managing the entire congestion control algorithm in the entire meta fleet. So last year we published a paper for this, and this talk is adding on top of that paper, where we will go a little bit into details on like how we are able to manage so many eBPF programs at meta scale. One thing to remember throughout the presentation would be our majority of eBPF programs are actively changing the status of the packets and the connection, not just actually monitoring and observing the states. Okay, so about us, I'm Prankur, I'm a software engineer. My partner in crime, Theo, unfortunately he has to attend an urgent teaching commitment in the Bay Area, so he had to skip the event. One thing, if I want to talk about myself, is I started by writing the Rocky V2 RDMA AI transfer protocol in assembly language into the NIC firmware. Then I moved on to the kernels, and now I'm doing all the network optimization at the user space level. So over my 12+ years of career, I have been very deep into the network stack. Good. So yeah, recently, well, again, recent is of course relative. A lot of companies have started adopting a BPF, a motivating factor being impressive performance wins. And now eBPF is becoming crucial for the cloud native workloads, especially in the AI area, where the demand of the cloud and the efficiency requirements are going off the charts. At Meta, we have had several significant wins across various metrics and the services. For example, we were able to do 40% improvements in the P99 latency for commerce and the search apps, 30% faster image generation, 100% faster storage read. A little bit of caveat, these metrics might be a little bit old, but I'm using it as it is because the recent ones are not made actual public yet. So, motivated by these wins, we want to use eBPF almost everywhere. So the graph here on the right actually shows the eBPF deployment. So at 99% of all our machines, we actively use eBPF by default. And we are constantly evolving our eBPF infra to support our evolving applications. The graph on the right here, we have at least it shows at least 2 versions of our BPF programs are being rolled out in a month to actually support our rapidly evolving AI services and stuff. So basically, to support a rapidly evolving BPF ecosystem, we need to build tools to rolling out frequently our eBPF changes into production with confidence, and they should be reliable. A little bit of introduction of eBPF. It's a technology in the Linux kernel that allows us to run the sandbox programs in the kernel space, enabling dynamic, safe, and efficient customization of a Linux kernel at whether it's networking, observability, or security. But the most important thing is it does it without you needing to change the kernel. So no reboot, no disruption of the host and stuff. Only programs that, so eBPF consists of these 2 main components, the kernel a verifier and the just-in-time compiler. Only programs that are passed through the verifier checks are allowed to run, which basically guarantees you whatever program you are loading it onto a host will not actually crash the kernel. So verifier provides that guarantees to you. And the just-in-time compiler translates the eBPF bytecode into a native machine code for the host CPU, which greatly improves the performance of your user space eBPF program to run as fast as the kernel code, which makes eBPF a practical for high throughput and low latency use cases. Now let's go into what are attach points or hook points. Hook points are where eBPF programs connect to the kernel to extend or observe its behavior. For example, TC, XTP, cgroup, syscalls, trace points, etc., etc. And we have eBPF maps. These are like fast and flexible data stores that enable communication and the data sharing for eBPF programs. So basically, these works as like a communication method through which your user space can program your eBPF programs with some policies, and then later on, if you want to like share a state across eBPF programs, you can use eBPF map to actually share that state as well. Okay, so now I want to like take a step on like discussing a concrete example of a eBPF related issue at Meta. So basically what was happening, it was a combination of like various things happening at the same time. We had like stacking enabled, we have like jumbo frames onboarded onto specific services, and we have like various eBPF programs running on a host which are doing MSS tuning and our own congestion control enablement and stuff. So with this, all of these things, we were able to like identify this entire combination resulted into like 5 distinct service issues. Few can be classified as like throttling, MSS mismatch happening, services seeing latency issues and stuff. Another thing was like Pixie started failing during like provisioning time. So basically it's an example. We will go at the later slide on like how we solved it and stuff. So when you are talking about like building an eBPF CI/CD pipeline, you need to account to like test for these like multiple combination of scenarios which can happen, and also build a proper reasonable tools for like monitoring and detecting a broad set of metrics for troubleshooting. And most important, we need to have tools for like fast recovery or mitigation. Okay, so basically eBPF changings can impact seemingly unrelated services, can have a huge blast radius, and these are generally really hard to triage until and unless you know what you are looking for and where you are looking for. So eBPF centric pipelines and observability tool are crucial to build the confidence for like pushing out these changes like frequently into the fleet. Okay, so in this talk, we will talk about like challenges and our solutions and like the observability. So first, I would like to discuss how Meta's rollout and the testing infrastructure works before highlighting any eBPF related specific challenges. And then we will go on to like discussing what tools we build to actually overcome those things. Okay, so at Meta, we already have a CI/CD pipeline infrastructure that works really well for like large microservices at scale. We call it a conveyor. This allows us to run specific tests designed by the service owners for detecting bugs and issues before production rollout. And during the production rollout, we use the standard phased out approach. We roll it slow and then catch it up later on. It's a standard trade-off between like speed and the safety. But for eBPF, the challenge here is with the test. We can definitely write a test, but there is no guarantee that what we are testing will actually hold into production or not. It's because of like a strong coupling between BPF and the kernel. We need to improve on this existing infrastructure and add new things to support our eBPF. Okay, so now coming on to like challenges. So here's an example. Unit tests, we all are aware these are like individual tests which run in parallel in like controlled and isolated environment. These are very helpful to like test BPF interfaces and specific code path, leveraging the homogeneity of our software stack, and they provide a very good signal before the code is actually committed. Here, one thing I want to highlight is like we have accumulated a large database of existing policies to manually generate a combination of like the packets and the connections, and so we can have a lot of combinations to exercise both the different code paths as well as the different options provided with the various eBPF interfaces. And since these tests actually run in like sufficiently constrained environment, we can validate their behavior and detect failure using like simple thresholds. Okay, So for controlled and isolated environment, the kernel provides us with like various services like C groups and the network namespaces, which are awesome for like few of the hook points like TC, C group and stuff, and will result in like testing what we want to actually test. But BPF requires like more new services because few of the hook points do not actually support like multiple programs with the same name. And when you are talking about a broader set of like the attach points which we use internally at Meta, unique challenges will come into play, which we will talk about here as well is in the next slides. So here's an example of like using the struct ops attach point. Basically, we use it to actually write our own congestion control into eBPF and then actually roll it out. So here the problem happens is like, since we have already rolled out our congestion control into the fleet, every host had that BPF program loaded. Now when we are running the unit test, which is again a service in like our container, it identifies, okay, I have the same BPF map already available onto the host. So the struct ops won't actually work as it is for a unit testing. So we had to like invent tools of like dynamically changing the name of our test BPF map to like run it and like verify whether it's like working as expected or not. So here on the graph on the right, what we are showing, it's representing the diversity of like BPF programs at like different attach points. At P75, we have like at least 4 attach points available at a time into Metascale. So significant diversity in kernel parameters provided at each attach point demands actually new tools. Again, an interesting case. In Meta, we actually roll out our kernel like really, really fast and crazily. So on the graph here, you can see like at P50, we have at most like 16 different kernel versions at a time into the fleet. And when you're talking about like a P90, we have like 100 plus kernel versions. And each eBPF hook point is essentially an insertion into like the kernel, so it's very dependent on the kernel changes. And since we have this like a heterogeneity in like the kernel versions, so services also gets this heterogeneity where a service can have like multiple kernel versions at a time in the fleet. In production and while testing, we have identified many instances where a regression into the kernel resulted in like weird behaviors of eBPF program. A point over here, we actually take the upstream kernel version. We don't have any in-house standard kernel version. So in essence, the heterogeneity of the kernels as well as the heterogeneity of the services thinks of like us to like think in like what additional things we have to add for building our pipeline. Yeah, this is also a very interesting challenge. So we talked a little bit about like how different teams owns like various different BPF programs, and most of the time they will eventually be attached onto like the same hook points. Okay, so here is a graph which shows like 50% of our servers actually run over like 180 BPF programs managed by like various other teams. We manage like 25% of the BPF programs out of these. So here the issue happens, right? So let's take an example of like the C group attach point. From the kernel point of view, they just provide us a standard a FIFO for queue. So whoever attaches actually first, it would be attached first and later on. So we have like multiple services starting onto like production host in various random orders, so that if they attach like ABC program on like host A, on host B, it can be BCA. So the order of these programs will change on host to host. But like I told earlier, most of our programs are actually changing the state of the connection and packets. And if other teams are also doing that, they will overwrite onto yours, they will step onto you and things. So things will go very, very weird into production if you don't account for all these things. So yeah, in order to test all these scenario, we needed to like try some shadow prod like behavior, basically. Okay, so now we will describe and go in a little bit details on like our various stages of our CI/CD pipeline. The first stage, it's a standard one, the unit testing. We are able to easily validate the behavior because the unit test environment it's like well contained, and we can use mechanisms like absolute threshold to actually detect failures. It just like plain load BPF program, generate the traffic, simulate packets and stuff, identify all the various combination of tests, and verify the code path is executing or not. Although these tests are very simple, but they offer one of the most accurate signals we have in our release pipeline. But again, the main drawback of these tests is a difficulty of like defining appropriate alert thresholds, which are not binary. Given the diversity of hardware and the service type, there is always a balance between like alert noisiness and accurate thresholds to detect actual problems. The next stage of our pipeline is integration testing. What we try to achieve in this phase is like do a coexistence testing between multiple features owned by our binary. So what we try to do is like we try to like reserve dedicated servers with a little bit of heterogeneity based on like either the hardware, the kernel type, the location, because we have like various services which require inter-region connections or like intra-region based on the scope of the connections. And here we try to like test like multiple features running concurrently onto a host. We generate like synthetic traffic between these hosts using iPerf and the netperf and stuff. Given that these servers are dedicated solely for the test, the challenge lies in selecting a small enough pool of servers to provide high enough diversity to explore all the feature-to-feature interactions. So in order to account for these, we took a little bit of measures with our next stage in our pipeline, which is called like production simulations. So the idea behind this stage is to like test production like setup, either from a host config perspective, like stack jobs, production like traffic, which can be like shadow workloads and stuff. So for example, on a stacked machine, stack machine is like when you have like multiple containers running on a host. So we try to like analyze whether our BPF programs are working as expected or not. When a service actually comes, we verify if the BPF map entries are populated correctly or not. And when the services go out, those map entries are purged right or not. Because this has a dependency on like other teams' binaries, as we collect various host attributes like the kernel version and all those things, the number of jobs running onto a host from them, we are able to like test compatibility between like the other teams' binaries with our recent changes and stuff. And in this stage, we try to extract early signals of our test by using other people's binaries as well. So again, the main challenge over here is, again, it's a relative approximation of production, and the shadow workloads are mostly controlled by the services, which may not be up to date all the time. Okay, so it's our last stage of the testing before we actually roll it out into production. It's our mini production release, basically. The thing which we did here was like, on daily basis, thousands of servers with the representative set of hardware types, the kernel version, and the services which have opted into like a dogfood tier, we tend to like roll out a binary and test. So basically assume like we want to like roll out a new feature which is specifically for a specific service. We try to like collect few of their production jobs and put it into like the dogfood tier, and on a daily basis we are extracting information of like how is our feature actually doing. Is the service behaving as expected after a feature or not? And in that we also mix a little bit with light. So like I told you, like other teams also control a lot of eBPF programs. So we try to like take hosts from their RC releases going into production into this tier, try to like do all the combination of testing to like have a little bit of understanding about like if our change will actually break anything which can be caught quickly or not. Here we also get a lot of good signals about any regressions into like the resource profile usage, like CPU, memory usage, regressions, and all those things. In previously discussed testing environment, covering all the possible hardware, kernel, and application traffic characteristics is a challenge. Here we try to address that by performing A/B testing on like production devices with like production traffic. One caveat with this approach is that any signal that is random or or if it takes weeks to manifest will of course be missed. For example, we had an issue where SS threshold corruption was happening into the fleet, but it took like 4 or 5 days to manifest into the fleet. We cannot actually catch it into a pipeline. Okay, so we talked about like all the challenges and what we did to like solve all those challenges and stuff. Now let's talk a little bit about like once we roll our binary into like production, what tools and the systems we had to like develop to understand how our software is actually doing it in production. So the first one is like for the short-term trends, exporting metrics to understand how is our eBPF program actually doing. So bubble up all the eBPF related metrics, the features, error counters and everything. One thing we learned the hard way was like don't put all your eggs in the same basket. We have to like decouple our metric collector, then exporter. Reason being another interesting use case. So here, as I told you, we are controlling a lot of connection settings into like the meta fleet. Now we want a data plane or our BPF to always be running while a control plane or binary may crash or being killed or whatever. So we have to like decouple our control plane with our data plane basically. So once you do that, we need an external service to extract all our BPF related counters, export it. We use like various inbuilt services to like export it to ODS, Scuba for like journal monitoring and observability and like building alerts out of this thing. So yeah, we basically extract all the data relevant for us to understand issues from like various other sources like packets, connections, RTT maps, stale entries into the map. Another important use case was like a feature was onboarded onto like this form reboot where we decouple the control plane with the data plane, and we identified like there was an issue in which the stale map entries are like remaining in the BPF maps. So, and the issue had like a huge blast radius because it was impacting all the virtual machines where we developers actually work. So whenever you want to like migrate a virtual machine, the traffic was getting black hole. Once we got an idea of this issue, we were able to like quickly identify the issue by extracting the BPF map entries, associate the time to live with those entries, and were able to like figure out, okay, this is an issue with the control plane being agnostic of the data plane. Okay, so we also have an auditor which validates the intent of a policy or a feature rollout. For example, assume like we are rolling out a new feature which is specific to a scope of a connection or like for a particular service itself. Our auditor validates the intent of the change and alerts if the intent is not honored. So we will have an auditor, we would task it to like, okay, if you identify any connection which is not part of this service and you're using this feature, raise the alert. The auditor leverages the data from like various external source of truth, the network telemetry, FB flow, and other things to reach to that actual decision. So it provides us to do an end-to-end validation over long period of time. Here's an example of like an issue where we got alerted based on like the violation of the data points and the criticality of the alert. As soon as we were able to identify the issue, we were see the steep line up, right? We were able to mitigate it really, really fast in production. So basically designing solutions and tools for quick mitigation is essential for eBPF infrastructure because like we discussed earlier, it can have huge blast radius and unintended problems at scale. So going back to our case study again, during this scenario, we identify our existing pipeline was not actually doing the things which we wanted it to do. So we had to like change it, add additional testing based on like the stack jobs and stuff. So we have to account it for that. So TLDR eBPF pipeline will always be continuously evolving due to like the increasing complexity of our use cases. And of course, the production will always be Wild West, new things will come into play for which we need to always be up to date and keep on evolving our pipelines into the future. Okay, cool. So so the key takeaways for the audience I would like to do would be like eBPF CICD will always needs tools and infrastructure tailored to your own eBPF use cases, and it has a larger, wider variable set. So different kernel interfaces, attach points, hook points, variability of like the different kernel versions, different expectations from the services for the same feature set, and multiple teams managing their own programs, which can overwrite or step on your programs and stuff. And issues will always cascade up and manifest in like various different ways. Not only we need to like build infrastructure for confidently rolling out our changes frequently, but also invest in like developing tools to actually troubleshoot these issues, and most importantly, help with like the quick recovery, because the blast radius is usually very high for these changes. Yeah, that's it from my side. I will open the floor for questions. Yeah. Any questions? Sure. So, so the question is like regarding about like how do we test a kernel? Yeah. So it's kind of taken care in a dog food tier. So basically, we try to like take the host where the kernel team is also actually rolling out. But at a time in our fleet, we have like 3 major kernel versions rolling out at the same time with like various minor kernel versions. So of course, we try to like take those into account. Also, we have this like a good VM testing framework in which like we have like these are part of the unit testing where we have like various containers installed like various VMs of like various kernel types. So we test it across all those things. But with the unit testing, it has its own caveats. We can only test like few of the things, but in the dog food, we are actually testing it in a production like setup across various kernel versions. Sure. Yeah, sure. Yeah. Any other questions? Sure. So the question is like regarding like if I understand it right, how do we monitor when we roll out our eBPF changes into scale? So like I said, like it requires the tools you have to like build based on your eBPF use case. So right now, most of the eBPF stuff in Kubernetes, what I was able to understand is mostly based on like observability and monitoring and stuff. Exactly, right? So those are like pretty straightforward. In my opinion, I might be wrong and stuff, but when you are talking about you are actually actively changing the state of the connection, meaning like we are actually changing the congestion control on the fly. We can actually bring the entire meta infra network actually down with like one change. So we had to like build tools to like highlight, to make it available to all the users and stuff. So you have to like build like specific tools on like how we are able to extract the right signals based on like RTT, because we are hacking. So it totally depends on the use case of the eBPF. So your tools will change because every attach point, every use of eBPF is like totally different. Sure.
Thanks for the talk. So I had a question regarding in a deployment, like how do you ensure that like certain hook points in eBPF can only have one program attached, right?
No, you can. Yeah, understood. So
yeah,
it's really hard. So it's a very deeper topic. I mean, like we have built our internal tools of like chaining all these eBPF programs in a particular order, and we have like built monitoring to understand if one program is trying to overwrite the other program's behavior and then export it and stop it basically. So building all these tools, we built our own eBPF chainer and stuff, which we plan to open source eventually, but let's see how it goes.
similar question about, let's say you have different teams developing eBPF programs. How do you coordinate? For example, like one program, let's say, stops piping packets to the next one, it can break everybody else.
Exactly. Yeah.
So do you have, you mentioned something internal tooling for this?
Yeah, so it was the same issue which we identified during a congestion control rollout. We had a security team, had their own eBPF program. They were not doing anything changes into the packets and stuff, but the return value they were passing was incorrect. So from the kernel point of view, if the reply field is actually 1, it will overwrite the results. So for that, we had to like enforce a particular ordering. For that, we had to like develop a user space chainer in which like we assign priority based on like, okay, how crucial is your setting? If 2 programs are trying to change one of the setting, who should have the priority? It would have a lower priority. And we also enforced it like if the other program in the chain is trying to change it, we will bubble it up through our monitoring and stuff, and we will stop it. So you should not actually do that. But again, we should not block it. So we have a pre-chainer and a post-chainer function which understands, okay, something along the lines actually changed anything, so it will overwrite it at the post-chaining function.
Thanks.
Sure. Cool. Any other questions? Sure.
Yeah, if nobody else has them. So about the observability, can you elaborate a little bit more on the metrics? Like what kind of metrics do you bubble up, and
Sure.
how exactly do you capture them?
Okay, so if you're talking about like from BPF infrastructure, all the metrics related to like failure of like attaching eBPF programs and stuff are owned by the control plane, so it will bubble up as part of the control plane. And we have like BPF level maps where for every function we increase a pointer or like increment a value into the BPF map, and we have like a data exporter which is acquiring all these like counter maps and exposing it so that we understand, okay, if the function is actually behaving the right way or not. But again, when we are talking about like millions of the servers, we have to aggregate it, and then the aggregator will take care of like stuff. Yeah. Cool, awesome. So I would be over here. It's outside the room. Feel free to like talk to me or ping me on my LinkedIn. Happy to answer any of the questions. Good. Okay, thanks a lot.